Yeah.
Yep, good to go.
Cool. Right. So I'm just going to go over the first question that I'll be doing with you guys now. So you're given this diagram, and so let me draw this. So the first question is, based on this diagram, you're given the parameters L equals 4.7 meters, R, or the radius, is 0.65 millimeters, and there's these two Y's here which run parallel to each other. So there's conductor 1 and conductor 2. Hey, just start if you haven't missed anything. So yeah, there's two identical cylindrical conductors, length 4.7 meters each, with a radius of 0.65 millimeters, and they run parallel. The center-to-center separation between the two is 3.6 millimeters from center to center. Center-to-center separation, and the medium is air. I don't have more pages. Sorry.
Swipe.
Yeah. I can just swipe back. So question A is, so the conductors are made up of copper with a conductivity of 5.6 times 10 to the 7 Siemens per meter, and a voltage applied at the battery is, or supply, whatever you want to call it, is 46 volts. And the load resistor is 49 ohms. So you want to calculate the current running through the entire circuit and the load side voltage. So the voltage back here, UR, is what we're trying to calculate. So we're trying to calculate current, I, and UR. So the first thing that you want to do is, whenever you're doing EMAG, the one thing that, it might be different now that it's in person, but when the tests were online, is they were really strict on making sure that you state whatever assumptions you make, or whatever information or whatever you're doing, make sure that it's thoroughly explained. So in this one, there's not really any assumptions that you're going to make, other than that the skin effect doesn't play a role. So you're assuming that that's DC and that the entire conductor is taking an equal amount of the current. Because you're using the, sorry, question. I'm not sure if I'm allowed to give it to you. This is last year's paper. If you haven't been given it, then you're probably not meant to have it. But I'll be just writing down every question that I'm going through. If you guys would want some time to try it before I go through these questions, I'm happy to, yeah, there's no midterms on your Moodle. Yeah, I asked some people before about that. I'm happy to give you guys some time to think and have a look at this question before, or I can just walk you through it. So do you want some time to think about how you would attempt it, or do you guys just want me?
I don't want to 2 hours, let's go for it.
Just go for it? Okay, cool, yeah. So the first thing that we need to do is draw a circuit diagram of our new circuit. So where the resistance here, our conductor, is the resistance of the conductive wiring itself. And then we have the load resistor here, which is equal to 49. So we want to try and calculate the conductive resistance so that we can then calculate the current, because V equals IR. So R conductor equals over sigma S. Oh, sorry. Let me. Ohms. And then S is the surface area. S equals pi R squared. So then from that, we can calculate the impedance of it. Or we can just go straight into here and say that I equals V bat over 2 times this, which is, oh, sorry, what term is it? Two times the length, which is 4.7 over the conductivity is 5.6 times 10 to the 7 times the surface area, which is pi 0.65 times 10 to the minus 3 squared. Sorry, this is going to be out of hand, and plus RL. And then you just have to plug in values for that and you will get the current. And that will come out as 0.936 amps. And then now that you have this current, it's pretty easy to calculate the voltage here. Voltage across the load equals the load resistance times current, and that's just 45.88. So is there any questions about that? That should all be pretty familiar. Yeah, double check my maths. But yeah, everyone is all good with that?
What did you say RL was, 49?
Yeah, 49 ohms.
Oh, is this for?
EMAG?
Yes.
Did I get a number wrong? No, all good, that perfect. Cool. So then for the next part of this question, so using the same diagram and everything, they want you to then talk about, so the current establishes a magnetic field and inductance forms between the two conductors. So they want you to calculate the total inductance per meter between the two inductors, ignoring the mutual inductance. So does anyone have any ideas about how you would do that? No, that's fine. So if you remember back to probably last week, I'm taking a guess at, you will have calculated the internal and external inductance. You guys have done that, right? You shrug of shoulders, right? That's looking good. Oh yeah, your midterm's not till after flex week, so you guys probably haven't even started studying yet, have you?
Oh, yeah.
No, all good. Right. Well, I won't go into the derivation much because Rukmi does it in the lectures pretty thoroughly and there's nothing more I can add to that. But you pretty much just need to know that the external inductance is equal to mu naught over 2 pi ln B on when I say ln, I mean natural logarithm. And that's henries per meter. And the internal inductance, which is a separate thing, is just mu naught over 8 pi. And that's completely independent of all parts of the wire. That's just every single wire has that internal inductance if it's just a pure normal wire. Yeah, so total inductance is just 2 times L internal plus L external. That's a pretty easy question if you know how to find L external and L internal. And yeah, there's nothing more I can do there other than tell you to watch how Rockme does it, because she's your lecturer and she obviously knows a thing or two about
So
this
in
subject.
your midterm exam, you have to derive these equations.
No, ours was online, so I just had it written right next to me.
Yeah.
You guys are in person for your midterm exam, aren't you?
Yeah.
I'm not sure what your formula sheet looks like. I don't have access to your Moodle.
So we have to collectively make up our own formula sheet.
Like it's just another share of like, we just have to put these.
Oh, right, well, then that's
So I have
perfect.
no idea if we're adding the right ones, the wrong ones.
Oh, right. So it's a collective sheet that everyone in the year works on.
Collective shit show.
Yeah, that sounds a bit like this.
That, inductance and phenomenon, it doesn't look familiar. I thought it was different, does anyone else? Yeah, I just thought it had more pieces to it. Am I wrong?
As far as I know, you are.
What's that, friend? You're
Yeah.
happy, alright, I'll shut up.
No, please. I am 100% not going to be right every time. But no, that's what the answers from last year's midterm are telling me, and that's what my own answers are telling me. So should be right. Cool. I'll go on to the next question because you might have missed it, but if we scroll back here to our diagram, the inductance is there's 2 conductors here. So we need to multiply the inductance by 2 because we've calculated the inductance of each inductor. So we're given L is the length of the total system, but the length of the wire is 2L. So therefore the inductance per meter of the system is equal to twice the inductance per meter of actual wire, because every meter the system is, the wire is 2 meters. Cool. Right, so I'll go on to the next question now. Right, so this one will be a little bit more familiar, hopefully. So it's a 2-wire system, has 2 identical copper conductors again. Each conductor has a circular cross section of radius r. So I'll start drawing this. Of radius a, sorry, not radius r, my bad. A, and the center to center separation distance between the conductors here is d. So you want to show that the maximum electric field along the line joining the centers of the conductor is E max equals rho L on 2 pi epsilon naught outside d over AD minus A. Can you all read my writing? Is it somewhat legible?
Oh, yeah.
It's on an iPad and my writing is not the best at the best of times, so I'm sorry about that. I'll try and fix it up a little bit for you guys. So the question's given us and we just want to show that. So, sorry, give me a sec. This one's pretty simple, just this formula, which you should all know. And in our case, the medium is we're assuming the medium is F. So E naught. Then from this, and that's for wire one. Looking back here. Oops, sorry. Looking up here, so we've got wire one, and wire two. And then similarly,
So what was the question asking?
so the question is asking to show that the maximum electric field is equal to this here.
Okay.
So show that. Cool, so we calculate it for the first wire, then we just go ahead and do same for the second wire, except the second wire is not just, ooh, I made a mistake. Sorry guys. Sorry, that's not that is row L, because it's the charge encapsulated, which is row L in this case per length. So for this second wire, we have row L on 2 pi epsilon naught, but instead of just the radius r now, if we scroll back up, we're no longer looking at the radius r to some arbitrary point over here. We're looking at the distance between the two centers minus r. So this length here is d minus r. Cool, and then just going to sum these two together. So the magnitude of the total electric field equals the sum of the two, which is rho L on 2 pi epsilon naught outside of 1 over r plus 1 over d minus r. And then from this, we will get those cancel out, and r side of d minus r. Yeah, and then so Emax occurs when r equals a. So we substitute in r equals a, and we find max rho L on 2 pi epsilon naught d on a d minus. Oh my god, that's horrible. Hold on, a d minus a. Yep, and that's what we had to show back here. Is there any questions about that? No one online has said anything. Right, cool. So now everyone's good. Yep. All right, so I will go on to the next one then. So this is part B of the same question. And it wants us to calculate, so if we assume that D is significantly greater than A, then we can approximate E max approximately rho L on 2 pi epsilon naught 1 on A. And that just comes in because if D is significantly larger than D minus A is essentially equal to D. So the two D's cancel out and you just are left with 1 on A. And that's all given in the question. You don't need to say, oh, let's assume that that's part of the question. And then it wants you to say that, so it gives you conductor radius equals 5 millimeters. And wants you to find the percentage errors of this approximation. So percentage error of Emax when D is 3.5 and 2 centimeters. So does anyone have any ideas on how to do that? No. Do any of you remember from first year physics a percentage error formula? No. That is a very fair assumption. I remember doing this question and forgetting the formula too. So yeah, it's something that you should probably remember. It will come up quite a lot throughout uni, to be honest, even though it's never like explicitly taught. It's just one of those things that you kind of expected to remember. I'll write it more generally, actually. So for some variable x that you measure, you have x measured over x actual minus 1, or alternatively, you do x measured minus x actual over x actual. And those are the same things. That's pretty basic algebra to prove that they're the same. So we're just doing that, except in this case, rather than x actual, we're using the Emax that we calculated in part 1. So we're just plugging in the values into, in our case, x actual equals rho L over 2 pi epsilon naught D on A D minus A, and x measured equals same front terms, but instead of D on A outside of D minus A, we're just doing 1 on A. So if you plug that all in, you will get that the error when distance is 3.5 centimeters. Error equals minus 14.3%. Oh, sorry, I forgot to mention actually, both of these are times 100%. You need to convert them to a percentage. So minus 14.3%. And when the distance is 2 centimeters, percentage error is 25%. Right. So can anyone think about why that percentage error might be higher when the distance is smaller?
Control.
Yeah. to that.
It's inverse, proportional to the measure value. So when the value of the B is smaller, the measure value will be bigger.
Yeah, you're pretty right. So pretty much our assumption was based on the fact that if we go back, D is significantly larger than A. So we have A equals 0.5 centimeters. Sorry, my bad, that was 2 centimeters. So A equals 0.5 centimeters. So the ratio of 0.5 centimeters to 2 centimeters is obviously much it's more impactful. So you're talking about a quarter of the measurement versus 1/7. So you end up with these pretty big differences in our calculated values. And then the question also asks you to calculate now the capacitance per meter across the two conductors, and then do the same and find the percentage errors between the approximate and real values. So, Gauss's law, everyone know Gauss's law? Not off the top of your head, you've learned about Gauss's law. If you go a formula sheet, that will be more than enough. So C approximately equals pi epsilon naught on ln D on A, or using the method of image, which again, I'm not going to go through here because you'll be able to just directly quote it. It's something that Rukmi derived in at the end of your first lecture slides or the start of your second one, I think. Just quote it for parallel wise, the capacitance is pi epsilon naught over natural log of D on 2A plus square root of D on 2A squared minus 1. And there's something careful to note here. There's multiple different types of these. So when you're talking about these different things, the D's actually have a slightly different meaning, and I've used the wrong one. So because some formulas will quote D as being the distance between the edges of the conductor. So if I draw my conductor down here, some formulas will use D as this distance, others will use it as this distance. So you just need to make sure that you're paying attention and you know the kind of way that the formulas were defined. Depending on the rules of your formula sheet, I would definitely recommend having a diagram that is labeled.
No diagrams? No diagrams.
No diagrams? Right. Then yeah, you'll just have to make sure that you pay attention to what distance is what, because some things require specific distances, and for memory, some of the labeling gets a bit messy at certain points. But for this one, both of them are the same. So you just have to quote these formulas.
That equation you've written there, you said that's the method of image equation.
Yes, this bottom one.
I'm probably other people in the same boat, but I don't know which equation to ever use. How do you use that one? How does a pool of equation that was given?
Yeah, you have to tell pretty much based on context clues, or in this question, it actually tells you use C approx formula that you found with Gauss's law. So you need to remember, because it doesn't tell you what that formula is. You just go remember which one was found with which method. So it says use Gauss's law for C approx. And this top one up here, it's Gauss's law. And then it tells you to use the method of image to find the more accurate version. So you just have to remember that this formula here is method of image. EMAG part A has quite a lot of memorization. Are you allowed to write on your formula sheet? I'm assuming you would be. It's probably worth labeling them. So saying that C equals pi epsilon naught on ln dA, and then like a dash Gauss's law or something. Because yeah, trying to figure out which one to use can be a bit of a pain. And that's where it comes down to, again, stating your assumptions. I know that in this test or the final, one of them, if not both, I use different equations at places compared to the answers. But because I wrote down, like for Gauss's law, assuming that the distances between the wires is large enough that like the interactions are negligible, then you're fine.
So which equation did you use in that instance?
Well, it tells you to use both in this question. Scrolling down, let me see if the questions in this test. No, it must have been the final actually. But there was one question in the final where it pretty much told you, hey, calculate the capacitance here, didn't specify how to calculate the capacitance, and you were given full marks no matter whether you used method of image or Gauss's law, as long as you could justify it. And as you'll see, the next question for this is find the percentage error between this approximate equation using Gauss's law or the actual calculated version using method of image. And when you calculate those differences, the percentage errors are actually, so at D equals 3.5 centimeters, the percentage error is only minus 1.08%. So if you're ever given a question that is two transmission lines that are like a centimeter thick wires and they're spread out by like half a meter, it's a pretty safe assumption that you can just use Gauss's law. Whereas if you're given a question about two PCB traces, for instance, that's my background, mainly in PCB design, you will have two traces that are incredibly small here, and your general rule of thumb is for width W, you space out your traces a value of 2 times the width of the largest trace out of the two. So in that case, using Gauss's law would probably not be a good idea because you'd get a reasonably large percentage error. But most of the stuff that you can do should be fine with Gauss's law unless stated otherwise. Questions will make it pretty obvious if they want to do method of image, because it will be a question that's specifically designed to assess method of image or solving differential equation approach and all of that kind of stuff. Yeah, if there's any ambiguity, just state reasonings and you'll be fine. So the other parts of the question, again, I don't really need to go through it, but I'll write it down. It's the exact same as the previous part. When D equals 2 centimeters, percentage error equal 5%. So just if you ever want to go back and do these questions in your own time, percentage error is 5%. And then it asks you to explain. Like if you were, so comparing the percentage error found back here when you're talking about the electric field strength. So where is it? Here. So comparing this percentage error here to our percentage error that we have for capacitance here, talk about when you would use the approximations. Like, should you ever use the approximation for the electric field? Should you ever use the approximation for capacitance? So does anyone have any ideas? Even just a comment on saying whether one approximation is more inaccurate than the other. No? All right. Yeah, so pretty much the error found back here in this question for the electric field, you can see is 14% or 25%. Those are pretty substantial errors, especially when you're talking about something from a safety perspective, which this is. You're talking about maximum electric field. Quite often that will be used to talk about like voltage or sparking, the breakdown of your insulators and everything. Pretty significant error to be having 25% off in that. Whereas if we go back to capacitance, having a 1% or 5% error is absolutely nothing. If you think about having two wires strung up going a massive distance, you're going to have more than a 1% error in the difference between what it says on the plans versus what it is in real life. Or if you're doing this in some other circuit that involves a capacitor, most capacitors, like the ones you guys used in your labs, the 220 nanofarad capacitors, that was a plus or minus 10% capacitor, which is why some of you will be getting pretty different errors. And plus or minus 10% is like actually reasonably good for a capacitor. Most capacitors that you use in electronic circuits for like decoupling and stuff, if you're doing 3106, they will all be like plus or minus 20% or more. So a 1 or 5% error in something like capacitance in this case is likely very much worth it to just get the maths out a little bit quicker. And that's pretty much just what you have to say.
With the percentage error, how do you know which one is actual and which one is measured?
So the actual one is the more accurate value. So it's one of those things again where you need to think about it. So if we go back to here, we're using this one as the actual one because it's the value that we calculated before making our assumption. And then we make the assumption that D is significantly larger than A, and we arrive at this formula here. So this is an approximation. And then going back here, again, this first one is an approximation of the second one. Method of image is actually solving it. Whereas when you're doing the approximation, you have to make assumptions that they don't interact with each other. So does that make sense to everyone? Cool. All right, so I'll move on to question 3 unless there's any more questions. No? Perfect. All right, so question 3, this one you will have done a million times throughout your course already, probably. If you've been going to tutes or anything, you're designing a cable with an insulating layer. So this cable has a single insulating layer. Let me write dot points. Single insulating layer. And you need to determine the thickness of the insulating layer for safe maximum operate and the safe maximum operating potential. So the cable has an inner copper conductor diameter of 10 millimeters. So it equals 10 millimeters, and this is of your conductor. And the insulating layer is made of cross-linked polyethylene or XLPE. And the dielectric strength is 20 megavolts per meter. And relative permittivity is 2.8. In this one, it actually tells you what your safety factors are. It's more common that you will have to assume a safety factor. So when I did the course, we were told pretty much assume a safety factor of 50%. I'm not sure if you guys have been told the same. Yes.
Or some question told us.
Yeah, cool. Yeah, normally the questions actually won't tell you what the safety factor is. You'll just get told, you will just have to write here, like assuming safety factor of 50%, because once again, state all your assumptions, very important in this course. So instead, it's a 55% factor of safety for the cross-linked polyethylene. Or an 80% for the air. Oh yeah, and it also tells you in the question, you can assume that the outside of the cable insulation will be at 0 potential. So that's an assumption that if not told in the question, you'll have to write down because you'll be assuming that with how you solve it. So this is what our cable is going to look like. So in the middle here is our copper conductor. A equals 5 millimeters. Yep. Which is just half diameter because you're given diameter. Make sure that you do that. That tripped a lot of people up, surprisingly, for this question. I know a lot of very smart people that just saw, oh, 10 millimeters and plug that into the formula. Formulas with radius, not diameter. So make sure you just pay attention to little things like that.
Will they still give marks for their process?
They were still given marks for their process,
yeah.
But they had, I don't know how many marks taken off. I'm assuming just one, but it's still 1 mark, which you really shouldn't have lost.
Yeah.
The main thing that I really can't stress enough is I know people that got a lot of marks taken off for not showing working and not stating assumptions. I've skipped a line or two of working here and there in these because the pages are kind of small and my writing's horrible. I'm trying to get through it because you guys don't have these questions. So if I get through it, I can at least show you all of the questions and you can decide to look through the recording later if you want to do them. But yeah, make sure that you show all your working and write down all your assumptions. And then we have the radius here of the cross-linked polyethylene, which is B, and we're trying to find B. So first thing that we need to do is, again, Emacs, this formula is used constantly. So Emacs equals rho L on 2 pi epsilon naught epsilon r. And where does the maximum electric field strength occur in this conductor? At what radius? Sorry, in this polyethylene. So we have cross-linked polyethylene here, and in here is the copper conductor.
The boundary between the conductor.
Yep, exactly. So what radius is that? A. Sorry. let me write this nice and neat for you guys. Radius of A. So A equals 5 millimeters. So R, which equals rho L on 2 pi epsilon naught epsilon R A. And this has to equal 55% of Emax. So we add a 0.55 out the front here, because once again, factor of safety. So we're told it has to be 55%, can't exceed 55% of the maximum breakdown voltage. So 55% of 20 millivolts, 20 megavolts, even 20 millivolts would be a pretty low breakdown voltage. So it comes out to 11, I think. Yeah, cool. So 11 megavolts per meter is rho L on 2 pi epsilon naught. And then epsilon R was given to us in the question. So epsilon R is 2.8. At least I think so. I didn't write it down here. Again, write down all your information. Yeah, relative permittivity is 2.8. I did write it down. ER equals 2.8. So 2 pi times epsilon naught times 2.8 times 5 10 to the minus 3, using SI units, of course. So that's 5 millimeters is 5 times 10 to the minus 3 meters. And then we want to, from this, our unknown variable is rho L. So we're calculating rho L. And from rho L, we'll then be able to go back and calculate the maximum electric field present in the air. So rho L equals here, so 308 times 10 to the 3. And then for things like this, leave it in terms of constants. It's one of the biggest tips I can give you. Constants that you know are going to appear up later in equations, rather than having these long, wild numbers. Just leave it in terms of epsilon naughts, leave it in terms of pi. Later when you're doing magnetism, leave it in terms of mu naughts until you're asked to actually give a value as an answer. Because as you'll see, when we try to calculate Emax air, that equals rho L on 2 pi epsilon naught B, because the maximum electric field for air occurs at radius B, where this here, where the polyethylene insulation ends, and that's your maximum electric field strength for air. And because rho L equals 3.08 times 10 to the 3 epsilon naught on pi, you can cross out both of these and then cross out that, and you get 308 times 10 to the 3, not 3.08, 308. And that leaves you with a much simpler equation. So then calculating B, it's 6.42 centimeters. And the thickness, again, this is another thing that people always get caught out with this question. The thickness of the polyethylene isn't 6.42 centimeters. Can someone tell me why? Exactly. So you calculated the radius value of B. Your thickness equals B minus A. And that is 5.92 centimeters. Again, it's just another really easy thing that you will lose a mark for when realistically you should get the mark. So just make sure to pay attention to that. And it also wants you to find the voltage. So completely forgot about that. So Vmax, pretty easy. Vmax equals minus the integral of d dot dr from A to B. Equals 393.1 kilovolts, if I've done that right. Cool. So that's all of class A. That was one question. So some of these questions can be pretty long. That was only worth 6 marks. Time will be another major factor. It's out of 50, this test. So that was about 10% of the test.
Open book.
Yes, open book. So our test was made to be harsher on time than I'm assuming your test will be.
Yours was last year.
Yeah.
I'll just got a reply from got me a message asking if you guys can show us given the question and solutions. Yeah.
Oh, perfect. Cool. The solutions are honestly not great. The ones that they've given us, I've been using. None of them have values, so I've been using my values for some of them. I didn't get 100% in this test, so you know. Yeah, I know, such a shame. So some of them might be off, but I'm giving you values that I think are correct. I went through and redid them, so it should be all correct. Yeah.
It's been hard to watch it without knowing the question actually is.
Yeah, so how can I send them questions? Yeah, can we send them now so that they can look at the questions?
That is awesome.
Yes. And once again, actually, the questions aren't even a PDF. The questions are just, because I don't have access to that either, it's literally a Moodle test that I was given. I might join on my laptop if you can send me, like email me the Zoom link. I imagine this. Yes, perfect. I will. Can I post images in the Zoom chat?
I think so.
Okay. Sorry, perfect. Thank you for asking that.
Thank you.
Or did she post questions on Teams?
Well, maybe I can do this. Do you have the question? I can take a photo.
Oh, you can take photos of the question. Yeah, perfect. That was question 1. Oh, you're gonna get my marks in.
Is this for like everyone? Or like, is this for later or like we're using it now?
Oh, both.
Both.
Oh.
So,
Are you looking at a website or the Moodle website? Or-
this is Moodle, yeah.
So we can't actually like PDF as you said.
I don't know if a PDF exists.
Yeah.
I,
I can take a look real quick.
yeah, of course, because I don't have access to your Moodle.
Yeah.
And this is literally just reviewing my Moodle exam from when I did it. That's the only way that I can look at the questions. So I think you guys would rather me go through this and just not be able to see them probably than me go through the tutorial questions that you already have answers to. This is probably the first topic. I don't 100%.
What question are we on?
Alright, we're up to question 3. Oh, the solutions are also in different orders to the question. Which is why every time I change questions, I'm scrolling through.
Do you have the PDFs of the answer of the solution?
Yeah, PDFs, the answers.
I'm glad we've all been given breaks.
It's not where it's not like all the artists has been what's the one I was
Thank you for that, because this is obviously my first crash course, if you couldn't tell.
no, it's pretty it's in my opinion, that's well, I need papers.
I get LSOC merch.
Ooh, what would be?
I don't know, I haven't asked yet. Yeah, hopefully a t-shirt. And I get to advertise with my race.
Yeah, exactly. It looks pretty good.
We applications open in term 3,
Is it?
Redback Racing.
Yeah, oh my goodness, good. But yeah, there's a high expectation on how many years obviously, right? If they join. So be hesitant because I'm pretty sure.
No, honestly, like courses help a lot, but a lot of the work we do is like course adjacent rather than just whatever you do in your course. It teaches you more about the courses and the courses teach you about it. But we 2133 was like my second highest mark, and I didn't watch a single lecture all year because I'd done all Schmidt triggers and MOSFETs and everything in Redback. 2133.
Wow.
Yeah. Right. Oh, we actually have questions now.
Yep.
Perfect.
And then if you want to add page, because now you can just click this one and add a new page. Because I also copy quite a bit.
Yeah.
Should be good now.
Yes. 2134.
Yeah.
Yeah.
What sort of, apparently that was all right. I was really bad.
I wasn't a fan of that one.
Really? It's 12, you got higher to 12.
Oh yeah. 2133. I really enjoyed it. Cool. I was also doing 2134 the same term as this actually, which probably made me hate it more.
Very lucky.
So cool. I can actually look at just the answers now. Right. Yeah. So you can see question A we've already done. That was the previous one. Question B now. So we want to just plot the variation of the electric field along radial distance. Must include numerical values and explain how you obtained them. So do you guys know what this graph should look like by any chance?
I get spiked, comes down a bit, spiked and goes down further.
Yeah, perfect. Because it's only a single insulating layer, it just spikes once. But yeah, so you have this region here. So I'll draw E in black. So this region here is nothing because it's inside the conductor. Actually, I'll draw it in blue if you something's a bit easier to differentiate. So this region here, there's no electric field inside a conductor. There's no electric field because the electrons move to oppose it. And then spike up here, goes down here, spike up here, goes down again. So this is E max XLPE. This is E min XLPE. And this here is E max XLPE. So when you're calculating these values, it's pretty easy. You literally just pull up your equation from before. So PL over 2 pi epsilon. And then this is radius R. So E max occurs when this line here, just so you know, it's a physics thing. It means given certain conditions. So E max given R equals A and epsilon equals 2.8 epsilon naught. And that gives you E max cross-linked polyethylene. So just E given that is E max cross-linked polyethylene. And that value, I'll have to go back to mine. That value was just the 11 megavolts per meter, which is what we were told to limit it to. By design, that's what we limited it to. E max air. E max air, once again, something that we limited it to. So we limited it during our equations to 2.4 megavolts. Because that is the 3 megavolts times 0.8.
It's a quick question.
Yeah.
Both supposed to be E max and both supposed to be XLP, or the second one's supposed to be.
The second one's meant to be air. Thank you. That's another thing that you would just lose marks for completely stupidly. Yeah, you would probably lose marks for that. For not 1 mark is dedicated to the neatness of the diagram, not just if it's labeled correctly. It's the actual neatness. So this is probably something you would lose marks for. So pick up on that. Yeah, so it goes up to 2.4 megavolts per meter. And then there's 2 ways that you can get this E min. You can either sub into this equation R equals B and epsilon is 2.8 epsilon naught. So you're essentially doing this same equation we did back. I've lost track of everything, sorry. Essentially doing this same equation you did back here, except instead of using epsilon naught, you're using epsilon R and epsilon naught to calculate the cross-linked polyethylene electric field at that point. Alternatively, assuming you guys remember your boundary conditions, you can literally just state that E normal on epsilon equals E normal 2 on epsilon 2. And from that, you can just calculate. I hope I got those the right way around. Yeah, you can just calculate, because cross-linked polyethylene has an epsilon R of 2.8, and obviously air has an epsilon R of 1. You can just say that it's 1 over 2.8 times the value of the air. So 2.4 over 2.8, 0.86 megavolts per meter.
Sorry, how do you calculate E min?
So you can either sub into this equation using your values for cross-linked polyethylene. So you can find E given R equals B, because this occurs at RB. So sub in
Oh, of
R
course, yeah.
equals B and epsilon R equals 2.8. Or you can use this, which is your boundary conditions. And your boundary conditions tell you that the electric field perpendicular or normal to the change in dielectrics is equal to, like, the electric field divided by the permittivity is equal. So electric field normal 1 over the relative permeability of field of the dielectric 1 equals the electric field 2 over the relative permeability of permittivity, sorry, of the second dielectric.
Yeah.
So that's doing literally the exact same thing, because this equation, if you switch between this and how we calculated Emax air, it's just dividing it by a factor of 2.8, because ER is 2.8 versus 1. This equation is the exact same thing, but you can just state it by saying, using the boundary conditions. Your boundary conditions when perpendicular are the opposites as well, just to keep in mind, something that helps. So perpendicular boundary conditions, sorry, not perpendicular, parallel boundary conditions. The tangent, I think, is what the notes call them. So the tangent electric fields are equal to each other. So because it's a not spherical, because it's a cross section of a circle, your electric fields are constantly going to be perpendicular to the dielectric change. Whereas if you, for some reason, had a square piece of cross-linked polyethylene, then your electric fields would be much, much more complicated, because it would start to bend and diffract as it leaves the metric, because the values going diagonal would remain the same. So I'll actually draw it here. So if you had square shielding and you had electric fields coming out like this, then this one would continue normal, but would be shortened, because you're going from ER equals 2 or some other constant, doesn't matter as long as it's higher than 1, to ER equals 1. Whereas if you had one that was coming out as a diagonal like this, this up movement would continue at the same rate, yet it would go out slower. So thinking about it the same way that light behaves when it goes into water, you observe diffraction, where the water, as light goes in, will bend down. And then when it comes out again, it will continue straight again. Or with prisms and stuff. This is actually why that occurs, if you've ever wondered. I'm not sure if you learned that in Phys 1B, I feel like you did. But yeah, because the electric and magnetic fields behave differently when they're tangential and normal to the change. Cool. And then question C, do you guys have any idea about cross-linked polyethylene is an imperfect dielectric? Do you know what an imperfect dielectric means? Right. I'm not going to make bold statements about anything, but in this case, the thing that we care about, the property of an imperfect dielectric that we care about, is that there's a leakage current. So an imperfect dielectric will have a leakage current, and that's obviously not necessarily a good thing in a cable that's going to be carrying high voltage. You don't want someone touching it and leakage current going through them, because it does not take much current to kill you. So this is going to affect the quality of the cable, obviously. Can you guys think of anything that would help to prevent this? yeah, wants you to make some recommendations to the cable
Second
customer.
layer of better material, you could increase the thickness of it.
Yeah, two good ideas. There's one other thing that was written in the answers as well that they wanted. So they actually recommended that you use shielding. So essentially create a coaxial cable and add a ground shield around it. Then any leakage current just flows through the circuit relatively harmlessly. The downside of that is that you would probably have to increase this or add in a separate dielectric that's better at blocking current or some other thing like that. Otherwise, in long transmission lines, you're going to get a massive amount of leakage current, and that's going to impact how your wires operate, because you might have 10 amps at the input, but by the time you reach the house that you're going to, 2 amps might have leaked out. And obviously that's a massive amount of power when you're at really high voltages.
Depends on the application.
Yeah, exactly. And these questions just want you to start thinking about what would you actually do in the real world. There's no necessarily right or wrong answer as far as I know. Don't take my word for it. I don't do marking. I'm not teaching the course, but the answers pretty much say just make sure that you add a shield. Cool. And so this is the final question. Oh, sorry, were there any other questions with that last one? Right, cool. Now you can actually see the questions. So what is the relative permeability and why do we use it instead of the magnetization vector? This is a really common type of question where they just ask you something about magnetization vectors, polarization vectors, or something that they know a lot of people don't understand. It's a question that's designed to be hard. Right. So I'll upload the answers and everything later, but I'll talk you through what I wrote for this question. My answer is nowhere near as good as the answers, but was still good enough to get full marks apparently. So just to give you a more realistic idea of what I think is expected of you, because the answers like derived and everything. So I pretty much say relative permeability is a scaling factor that relates to the permeability of a material to that of free space. So it's a scaling factor that changes, that tells you about how the material behaves compared to free space. Pretty simple. So magnetization vector is a measure of the induced magnetic dipoles within a material due to a magnetic field. The magnetization vector isn't used. You writing this down? The magnetization vector isn't used as it is much more difficult to measure and can be replaced by the relative permeability mathematically.
Did you know that?
When I did the course, yes.
How the fuck do you know that? I'm doing the course, man.
I can't remember it now, but
I see what that question is. Didn't it?
Yeah.
oh, did you put in ChatGPT? Yeah, and it also wanted you to do, as a bare minimum, it wanted you to do a little bit of maths to get full marks. So it wanted you to just do so it wanted that for full marks.
So what I'm getting is you can get half marks if you just define what relative permeability is.
Yeah. you can get over half marks if you just define relative permeability and kind of talk about magnetization vector briefly, you can get decent marks. They're not trying to like strip away all your marks. They're trying to differentiate.
I'd argue differently, but sure.
They're trying to differentiate your top students from your people that have done a bunch of practice problems and know how to solve the problems, but don't really have a great understanding of the concept. Because in case you haven't realized, a lot of these problems have been almost direct copies out of tutorial problems. In fact, last question you would have done multiple times. You literally spent like half a tutorial on finding the like width of dielectrics and stuff that would give you certain factors of safety and certain voltages and everything. All, yeah. They want normally at least one question that will probe into a deeper understanding. So all you need to do is just the night before, have a read through the lecture notes and try and just remember a few basic points about these things, and you'll be able to get a decent number. You'll be surprised how many people see this and just go, oh yeah, not doing that.
Yeah.
Yeah.
Yeah, this is.
Yeah, what's your answer?
Is relative permeability is you need less measured permeability of the material to support formation of the magnet relative to the ability of the vacuum tubes. That's similar. It's used instead of a magnetization that allows a direct comparison between the materials and the effect of the magnetism. It also allows for comparison between different magnetic fields and your effect on the material.
That's what I find now.
Yeah, it's used because it's much easier to measure. In this course, there's nothing that you really want to do. If you start going into thermodynamics, then magnetization vector starts to have an actual use, but yeah, for the most part, relative permeability is fine. The mean length of a steel core of a toroidal inductor is 4 meters. So cross-section area of the core is 6.8 centimeters. Relative permeability of the core steel is 5,400. The applied MMF is 22 angstrom is 18. I can't remember what that unit is. Sorry. Calculate the flux density in the core. Assume uniform flux density. So again, if you were ever given this question, you would have to write assume uniform flux density. They like to tell you to assume things so that someone doesn't go on a massive tangent and like derive half of EMAG. I don't know, there's some very smart people out there that do a lot more than I did.
Oh, yeah.
So
So just writing down the key information first. So your length, your cross-sectional area, MMF, which is magneto something force. Mu R, relative permeability. Cool. How much magnetic stuff have you guys done? Like, not how much has the course done, how much have you actually done?
actually, it's quite a bit.
Yeah, I will just write down my working then and probably won't go into too much detail explaining it. That way you guys at least have this written down. If you ever want to look back on it. So you're pretty much just treating it kind of like a circuit for a lot of this stuff. It becomes pretty basic circuit analysis things where certain properties of the material or whatever are analogous to current or voltage and resistance, those kinds of things. So you end up with a pretty simple equation mathematically. You just have to try and remember what's analogous to what. And that's not my normal R, by the way. I know my writing is a bit messy, but that's some special R that is written kind of weirdly. So yeah, you're trying to find this sigma, and then from that you use B equals that over surface area, which gives you magnetic field, millitesla. And yes, that's your answer. Oh, I forgot the step actually. So over here, R equals inductance over mu S, which equals 4 over. That's in millimeters, so it's times 10 to the minus 6. Cool. So yeah, there's not going to be any questions on that, obviously, if you guys just haven't done it yet, which fair enough, your test not for a while, and you're all third years.
Yeah.
So you just, are any of you doing BEME, or are you all having to do tele?
Sorry.
Are you doing BEME, like the degree, the masters?
Oh, actually, the master. No,
No,
no.
right. So yeah, you would have been doing tele as well. Your tele midterm was yesterday. Midterm. Yeah, wasn't there a tele midterm?
Yeah.
Yeah.
It was pretty bad. Some students started like 10 minutes earlier.
Yeah, I heard about that.
Oh,
Yeah. Cool. So yeah, you've all been focusing on that and not studying on this. Don't blame you. Question C, if a small air gap of a few millimeters is introduced into the core, will it have an effect on the core flux density? Why or why not? And is that desirable? Based on what you guys know, can you give me an answer for that?
It definitely will. I'll explain why. So we're expecting there's no leakage, no fringing, so surface would be the same. The flux would be the same. But what is different is the reluctance.
Yeah.
Through the conductor and through the gap. And it's desirable. Why? That's magnetic, so it's that.
Yeah, I don't know.
Yeah. So it is you changing your reluctance? Because
Yeah,
the permeable.
Oh,
Yeah. So it's increasing your reluctance. So that will decrease the flux density because you're increasing reluctance. It will help prevent saturation. Interestingly enough, 2134 this year actually has an in-person lab. Just one lab. So their lab involved they went into the EMAG lab. They used inductors, and there were 2 different types of like power inductors, and they were doing power factor calculations.
So they actually have experiments to do.
Just one in the first place. it was not, it was like, all right, it was a really good learning thing, but I don't think many of them enjoyed it. It wasn't particularly fun. But yeah, so they went in and there were two different types of inductors, and the people that were unlucky enough to get a certain type of inductor, both the inductors were both rated to 0.5 millihenries at 10 amps, except one of the inductors was a really old inductor design. So it actually at 10 amps, the core started to saturate. So when we were running 1 amp through it during the experiment, their inductance was closer to about 80 millihenries is what I calculated. So
Yeah.
a reasonably big increase, because compared to the 50, like, so they were getting significantly different results and everything. So yeah, things like air gap, if those have been designed better to avoid the core saturating or anything. Yeah.
Saturation makes it plateau.
Yeah, so because at 10 amps, it saturated, the rating was based on the inductance with a saturated core. So when we were running it at less current, it hadn't plateaued yet. I'll do it online so people can see. So your graph kind of looks like this. From memory, I hope this is right. So
New inductance, new wires.
yes.
Yeah.
So at 10 amps, they were kind of off here with 50 millihenries or whatever the value was. This is not inductance, actually. This is inductivity, I think it's called, but it's pretty much inductance divided by current. It's the ability for it to be induced or something like that. Ooh, I should have reviewed more for this. But yeah, so they ended up in this region where it started to saturate, and then when they were measuring at a much lower current, the core hadn't actually saturated yet. So they were getting this nice 50 millihenry inductance. Yeah. Do you guys have any questions that you want me to go through and just explain about the course? Anything from the earlier questions? Now you can actually see what the questions are. Is question 1 here?
I saw it as well.
Oh yeah, question 1. So that's a little bit better than my drawing. Do you have any more questions about that? No. Oh, this is showing you one question that I didn't go through actually. Question 1C when we did ours was topic of debate. When I give you the answers are very unusual, to say the least. As far as I know, most people were just marked correct, no matter what they drew, because the answers were like, so I'll remember the question. So you're drawing a circuit model for the system. Oh, cool, I got paper right here. So the answers, I remember what they were pretty much. The answer said it was something like this, where you had R conductor, R load, going back over to R conductor again, and back to your input source. And then they drew in here Oh, I don't know what happened there. They drew in here, inductor, resistor. I don't know why it's doing this, sorry. And then inductor again, and that was L external, and then leakage, and all sorts of weird things. They had capacitors and inductors in ground. I'm pretty sure that this is wrong. When I publish the answers, you'll see what it was exactly. This is not like, if you know the transmission line model of a cable, something that's really common, it looks like this. So that's what a cable looks like as a transmission line. And you'll notice your inductance is in series with your resistance, and then your capacitors in parallel. And that means that your inductances don't short out your inputs. Yeah, there's lots of weird stuff going on with that one. So as far as I know, I definitely drew something that was different and got given marks for it. I know someone else that I spoke to about this because I was worried someone was going to ask me about it. I spoke to them, they drew something completely different that was much closer to the transmission line model. They got marks correct as well. Is probably worth knowing this transmission line model. You'll need it for part B of the course anyway. And electronics. That's why you are doing electronics. No.
And this is like,
Oh, I'm loving electronics. Electronics is like the thing that I enjoy though. So pretty much when you do electronics and later on in this course, you'll get reflections going on, and it all happens because of the characteristics of this transmission line, except you take it infinitely small and like make them all in series. Cool. Do you have any questions or anything else? Because that's everything that I planned to go over.
that was great, yeah, because I haven't. So I don't have any questions.
Yeah, that's probably why you think I'm doing a good job, honestly.
Did some exam incorporated question fill from every part of our engines that are summary with all. But we get questions now.
Yeah. Yeah, how should I send them solutions to these questions?
You say there's a PDF.
Yeah, I've got them as a PDF. Do I just pop them in the Zoom chat?
Oh, you just send them to me.
Right.
Oh,
Yeah, and then everyone signed up, so you can just email it. You guys get exclusives. Cool. And you'll just send them these notes as well that have the questions on it. Cool.
Yeah, it's
You want me to talk about some of that stuff?
yeah, because they're kind of like talking
Integration. So direct integration, is where you talk about how you need to simplify it down to one dimension. So it's inevitable to say that like the version line in finding the cable that the direction the cable is going. I don't think we actually ever got tested on direct integration.
too easy.
Yeah, it's
One direction.
yeah, method of image. There's nothing I can tell you about other than look means derivation. Pretty much just have to find I've got the iPad so that people can hear me talk. Wait, is it iPad or laptop that?
Laptop.
Oh, that's plugged in. I'll just have to
You can just
talk about it from here, I guess. Oh yeah, we don't need the screen anymore, so I can just unplug it. Cool. You're coming with me, people online. So method of image, yeah, Rookme's derivations are the best source of information for that. You mainly use it for parallel cables, and you just saw the formula earlier.
Yeah.
As far as I know, you can just quote it unless specifically asked to derive.
Sweet.
So with the method of image, when you have an infant on ground plane, what you do is you assume it's on your opposed image.
Yeah, so
Then
you
you get the capacitance and you divide it by two, because it really only one.
yes.
Yeah, that makes sense.
Yeah.
Is the cylinder one any different?
What do you mean the cylinder one of separation
You
of
have a
variables?
charge as an example, but
Yeah, it's just remembering batches.
you want to share?
No.
Yeah, that's with a single charge.
Yeah, so you insert an equipotential surface. So for a single charge, insert an equipotential surface, find the capacitance. Or when you're doing like the complex one is when you're doing two parallel lines.
Is that not what our question just was?
Yeah, it was. I just quoted the formula for you. But if you want to actually derive the formula, it's a pain because you have to know that you have to find a circle that has an equal potential around it. So find equipotential surface and then walk through this and yeah.
Let's remember the
Yeah,
formula, write
if
it
you've
down.
got formula sheet.
I'm happy to lose marks.
Yeah, oh no, same, yeah.
No, I derived it like a once for practice,
Wow.
just following
Annual
Rookme's.
sorry.
Yeah, no, following Rookme's, not because
Oh.
no, fun. I wasn't seeing it like no, I'm bored. Let's derive it.
Bored on a Friday night at the clubs, yeah.
Yeah, isn't that what you do at nightclubs?
First one to get it as a shot.
Yeah, sweet.
Yeah, honestly, just remember the formulas if you're confused about it, because it is useful again here. Like there's multiple D's and multiple P's and multiple R's, and trying to remember, just remember which D is which or which one is which, and you'll see in the formula like the only one that matters here is center to center when you actually use the formula, because that's D. So that's fine. That's, you just need to remember method of image, center to center. Some of the other ones I think were a little bit different. And then your last method is separation of variables.
Yes,
Yeah, that one.
I had a bit of trouble actually. I don't know how to describe it actually. See it first.
The separation took a while for me to understand. I remember then.
Okay. Does it get easier from here, by the way? Or does it get tougher?
It
The
gets-
topics
Like in what?
in just
In this course.
yeah.
Part B is completely different. It's, I
Electromagnetic.
found it a bit harder but easier at the same time, if that makes sense. It was easier like to do the questions,
Right.
but there were more questions you could be asked on, whereas
Oh.
this, there's like a very small number of
Oh.
questions. So once you've done a few practice questions,
You're
you
set.
can go into the test and you know you're going to be
okay.
able to get like
Well, thanks for the
minimum
heads up.
60%
Yeah,
or something,
sweet.
because you've done almost all the different variations of questions that they can ask. The tutorial questions are amazing.
Sweet.
They're literally almost
Alright.
direct copies with different values.
Can't really do it properly.
Yeah. So it's in the past.
Yeah, process is not bad, it's just understanding is a bit of trouble for me.
Yeah.
You know what that is?
So it's second order differential equation, two-dimensional differential equation, and you pretty much just need to separate it into a differential equation for each kind of area. And the best way that I found was just following this example, and it was a bit confusing, but you just find differential equations and then you know boundary conditions. So you solve the differential equation at the boundary conditions. So you say at x equals 0, v equals 0, and that x equals a, v equals 0. And therefore you know that you're going to have a sine wave or some permutation of sine waves. So it's either a straight sine wave or it's like an nth harmonic of a sine wave. And yeah, then you sum those up or something. Yeah, so it's two-dimensional problem. Yeah, so you know that it's going to, the y-axis in this question is going to be exponential because it starts at 0. It starts at v0, sorry, and goes up to 0. So you just solve the y-axis independently, and then you solve the x-axis independently, and then you kind of merge them together.
Oh, okay. That's
Yeah. It looks complex, but once you've done it once or twice, it actually becomes pretty simple, and you just kind of follow through doing the same thing over and over again.
okay.
But yeah, like I said, I don't think we actually got asked anything on this, which is probably why my numbers are a little hazy.
Fair enough. Yeah. Yes, sweet. But yeah, I do have a question about, sorry, if I scroll up. Don't do too much. I think I have it on my iPad. It's regards to the workshop. Interesting thing, I think. Yeah, so we had to, so here, in this example. Yes, this one. So in this example, we're using methods of separating variables, and the voltage is only changing in z in respect to z. So that's why the cylindrical coordinates we only need to care about. We only need to solve for this equation. So when I integrated, this is probably simple math, but I forgot how integrating this works. If I integrate the left-hand side, does it just become v? I don't know why. So.
Wait, so
What are you integrating with respect to?
It's like integrating one, but yeah.
So you're integrating dv and you get out v because you're saying this is a partial differential equation. So you're saying dv is equal to something dot dx dz. Take the double integral of dv is just v, and then the double integral of dz squared will be some equation that tells you how something varies.
I'm just not sure how we got from this. It's probably just simple math now.
Yeah, it's just integrating it. You just need to know that when you integrate it becomes v.
Okay, all right. I just had to remember that. So it just so it seems to make sense. I think it's all and also when we integrate the left hand side, why isn't there a constant we should care about for integrations without knowing the
because of the boundary conditions, because you're then solving this later. The boundary conditions mean that there's no constant.
Fair enough. Okay, sweet. That makes a lot of sense. That confused me quite a lot before. Do you guys have any questions about this? This is
Why isn't it d squared v? Why does it become v?
That's my question.
Yeah, so
apparently
d squared. Is this the double integral, or is this working that she's done, or is this?
That's what I've done actually. So it's probably wrong.
Has she released solutions for this?
No, God, no.
There was a recording workshops, and then you can go
Yeah,
through it.
the recorded workshops.
Do you have Teams
the
on your
solutions
laptop?
for it.
They have it on Teams.
Oh, did you?
But
Yeah,
I'm pretty
the
sure she went
demonstration
through
is-
this.
The
Oh, you don't?
tutorial questions that have the answers are much
Yeah.
more used than the workshop ones.
Sweet. Then shouldn't waste time on that. Yeah, but definitely we have to integrate this, so we just need to know.
I wrote my massive notes from when I was in course.
Just stop the recording.
Oh, yeah.
Question.
This was for question, well, question 1.